So, as you had seen basically in the preface to this video, as well as back in near chapter 3, the way to find the perimeter of a circle, or at least the early methods of finding the perimeter of a circle, were just to use inscribed or circumscribed polygons. And we're now actually going to be doing that. I'm not going to show you each and every detailed construction, but we will kind of go over what kind of some of those results are. And in the previous picture, you kind of saw how when you had the triangle, there was a lot of extra area. When you had the square, not quite so much area. And then as you kept on getting more and more sides to fill that circle, okay, progressively the amount of space that wasn't accounted for between the circle and the polygon was basically diminishing. So you've got two things going on. Your polygon is filling up your circle, and it's also getting approximately the same perimeter, okay, as it keeps getting more and more sides. This was basically the method in which they found what pi actually was. They knew there was a relationship between the length and the radius, or the circumference and the radius, but to actually understand what that relationship was, they had to kind of derive pi this way. And this is the way that was employed by Archimedes. So when we do it, we're actually going to be using more of the apothem equation that we were using before, where the number of sides times the side length times the apothem over 2 is going to give us our area. Okay? And I'm just going to list most of those off here. We're not going to derive them. You've either seen them in prior videos, or you will be deriving them in either exercises, or they're just too difficult to find inherently. Okay? So we're going to talk about, let's say, the triangle. Okay, and I'll scroll this down a bit so you can see. Triangle, which has 3 sides. Okay, and we're going to be talking about inscribing this in a circle. Okay, not drawn with the compass because we're not trying to be exact here, of radius 1. Okay, so think of the triangle that would actually fit in there. Of course, we need an equilateral triangle to make all things very nice. All of these are going to be regular polygons. Okay, the side length of a triangle that does that, the side length, okay, along with the apothem, okay, and then the corresponding area are given as the square root of 3. The apothem is 1/2. Okay, and then the area is approximately 1.3. Okay, so we know that from having a circle and having a triangle in there, okay, there's a lot of extra space that we're just not accounting for. All of this stuff. Okay, so this area that we have here is really an underestimate. Okay, if we go to the next one up, the square, okay, the square is the next regular one, we have a side length of root 2, an apothem of 1 over root 2, okay, and an area of 2. Again, the area just comes from this equation. We know the number of sides, we know the side length, and the apothem. Divided by 2, and we'll have the area. Okay. So, if we keep going on, we've got pentagon, hexagon, septagon, octagon, all the way on down as far as we can get, and we're actually just going to measure what it is for a 50-sided object as well. So when we have the pentagon, the regular pentagon, okay, something along this shape, hexagon, okay, heptagon, and octagon, which is your familiar stop sign shape. Okay. And I'm not even going to attempt to draw the 51 in the event I would probably bore you. So each of these has the radius distance, so from the center of the polygon to the vertex is given as a radius of 1. Then we know what the sides are going to be basically by doing our triangle constructions and subdivision that we were doing before. So our sides are given as, and I'm just going to write out the decimal form at this point, 1.176. The hexagon is 1. Okay. The heptagon, or septagon, is 0.868. and the octagon is 0.765. The 50-sided object has a side length of 0.126. Okay. The apothegms as given are 0.809, the 0.866, 0.901, 0.924, and 0.998 for the 50-sided object. Okay. If we apply this formula to each, we will find that the area ends up being 2.736, I'm sorry, 2.378, 2.598, 2.736, 2.828, and 3.133. Now, remember, the area of the circle of radius 1 is just pi times 1 squared. Okay. So we're expecting the area to approach the value of pi, which, as soon as we get to about 50, is pretty close. Remember, pi is equal to, or approximately, 3.14. Okay? So we're actually getting rather close by the time we get to 50. You can imagine how much time it took to do all of this by hand. Okay? What about the perimeter? Well, the perimeter is just going to be what? It's going to be the number of sides times the side length. We're just going to do that for the 50-sided object. So the perimeter is equal to 50 times 0.126. Okay? And if we do that, 6, the perimeter is approximately equal to 6.3. Okay? The perimeter, when you do this, okay, is approximately equal to our known 2 pi r, okay, which, when the radius is 1, is just equal to 2 pi. Well, 2 pi is 6.28. Okay? So we're actually doing relatively well at this point as well in trying to find what value of pi we should have. If we divide this number by 2, we find the perimeter, or the value for pi, so you divide both sides by 2, knowing that r is 1, we got 3.15. Okay? Which, just like in the terms of the area guy, is actually relatively close, okay, compared to these guys.